I'm going to give you the scenario of why this is going to be important to us. So we're going to have a business situation tomorrow that looks at the following. We want to roll out a new product. All right, we're going to roll out a new product, and the new product could be very successful, could be a moderate success, or it could be a failure. Oh, that's not something we control, so it shouldn't be a decision, right? The decision is whether we roll it out or not, right? The outcome is very successful, moderately successful, or a failure, all right? So it could be a new product, or it could be like a TV show or something like that, right? So our decision is going to be roll out or not, right? So in many cases, especially true in television, but it's true for new products as well, before you roll out a new product all the way and spend all the money to roll it out, you may want to do some market research up front. So you want to collect some data from the market, from a small group, and ask them what their opinion of it is. In television, they do this at several levels. They have small groups of people read through the script to see if it's any good. Then if the script gets made, they make a few TV shows. They don't show it to anybody but a small private group. If that works, then they do a pilot for a couple episodes. If that works, then it becomes a TV show. So there's several tiers of this. All right, so you see the example. So we're going to have another decision up front of whether we collect sample data or not, right? And the reason you collect sample data is so you can get better information on whether the product's going to be successful. So after you collect the sample information, you're going to say, focus group says yes, or focus group says no, right? Not a good product, right? You still, in any case, have the decision of whether to roll out the product or not, right? No matter what the focus group says, you still have this choice, right? However, if you think about it, given what the focus group says, it might affect the probabilities of the product actually being successful. In other words, if the focus group or the sample, whatever sample you're doing, has any valuable information in it at all, right? If it has any valuable information at all, that could change these probabilities, right? So on this node, you're going to have the same very successful, moderately successful failure, right? But these probabilities could be different from these probabilities because the sample information in here said, yeah, that's a good product, right? So there might be a higher probability of being very successful and a lower probability of failure, whereas down here they said, no, that's crappy. So there might be a lower probability of being very successful, right? And so essentially what you have here is a two-stage decision problem. You have one stage right here where you're collecting data, and you have another stage here where you're making the actual decision, but the probabilities of what happens in the decision part depend, right? That's the important thing. They are conditional upon what information is gathered up here, okay? So we have this idea of conditional probability, okay? All right.
I mean, we're just putting weights on the probabilities, and that's it.
Yes, but let me give some concrete numbers. So if the focus group says it's going to be successful, right? Then we roll it out. We have a 60% chance of success, a very successful 20%, and 20% chance of failure. Okay? But if the focus group says it's not going to be successful, we have a 40% chance of being very successful, a 40% chance of being moderately successful, and a 30% chance of being a total failure. Okay? Notice how these probabilities are higher based on what they said, and these probabilities are lower. Now, even if they say no, you may still do it, but you know your expected value is probably not going to be quite as high, right? And that's what we're going to see tomorrow. But the point I'm trying to make is that these probabilities are conditional on these probabilities.
When you meet tomorrow, you meet them test-wise, or?
No, we're going to go through this in a lecture, okay? So do you remember about conditional probability, probability of A given B?
We will have to face this on the final, right?
Yes, on the final.
Okay.
Yes, on the final.
Face is the correct word.
Yeah, face, exactly. Okay, probability of A given B is defined as the probability of A intersect B, A and B, right? So remember this means and divided by the probability of B. That's the definition of conditional probability. So given I know B's occurred, what's the probability of A? Given I looked out and it's cloudy, what's the probability it's raining? Well, the probability of rain is higher when it's cloudy than when it's sunny, right? So if it's not cloudy, there's probably a very low probability of rain, right? So you look at all the times when it's cloudy and raining, and you divide it by the times when it was just cloudy. Right, that's how you calculate that. So that's the standard definition. I'm sure we covered this. Okay. All right. If you just a couple other things. Another way to represent this is you can say in a little table, right? You can say A and A complement, which is like not A, and then you can say B and B complement, which is not B. And we're going to do a concrete example in a minute. Everything adds up to 1, right? This is the probability of B down here. This is the probability of B complement. This is the probability of A complement. This is the probability of A. And again, A complement just means not A, right? Right? So you may not remember this part, but these probabilities are the joint probabilities. It's the probability of A and B both happening. This is the probability of A and B complement. This is the probability of A complement and B, and this is the probability of A complement and B complement. So we call this the joint probability table. And one of the secrets is, of course, if we know the joint probability table, we can compute any conditional probability we want to calculate. These conditionals aren't in here, but we can use this formula. Yes?
This is not something generic, correct?
This is something generic. This is something generic. Yeah, this is something generic. All right? Okay, so I haven't told you anything about Bayes' rule yet. This is just a warm-up. All right? I'll write the formula for Bayes' rule, and then I'll try to explain to you why it's important and how it relates to this tree. Then we'll try to see if we can use Bayes' rule to solve this problem, okay? So this is probably going to be partly like getting the rust off and partly new, okay? So in Bayes' rule, what we're doing is we're doing the probability of B given A, and this is the probability of A given B times the probability of B divided by the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. Now, most of the time when you show this to students, especially MBAs, they're like, right? We have this expression in English. I don't know if you guys use it. WTF, right? Okay, we'll scribble that out, right? Okay, so let me be clear here about what all these things mean. Probability of B, right? So this is how likely we thought it was going to be to rain today when we watched the news last night, okay? So we call this the prior probability, right? And actually this probability of the prior is occurring there. It's also occurring there in the formula and there, right? Because probability of B complement obviously is 1 minus the probability of B. So these are our prior beliefs. Now that we're 3/4 of the way through the day and we look outside and we see some blue sky anyway, right? We have some information about the weather on that day. So given what happened, what we saw, we update our probability of rain, right? Probably today we would reduce it, right? So this probability down here is called the posterior probability, right? And then these other terms here, these three, they're all kind of the same thing. These three. These are called likelihoods. And there's good argument for why we might actually know the likelihoods. By the way, this is a little hard to implement for the average Joe, but there's good reason to know why we might know the likelihoods. Let me try to give you the weather example. So let's suppose, again, B is the event of rain on a given day, and A is something about, I mean, if you're a meteorologist like my father was, the kinds of clouds that are in the sky, okay? Or A could be, what's the air pressure, right? Because we know when the air pressure is high, you know, like around 30 millibars or whatever, then it's gonna not be bad weather, but if the pressure drops, that's when we have bad weather. So A is some other piece of information about the weather. But let's suppose it's us looking out the window and sort of sizing up the day. Whatever it is, right? This is the probability it's gonna rain before the day begins. And given what we saw, this is now our probability of rain. So we update our information. Why would we know these, right? Well, on all days when it rained, what did we see outside?
Clouds.
Right? So given it rained, what did we see outside? If you were keeping track of your observations, you would actually know that. On every cloudy day, what percentage of them did have clouds like today, right? You would actually know that.
That's built on empirical data.
Yeah, this is built on sort of historical information, okay? All right, so you make any estimate in a sense that you want for the prior. You gather this additional information. If you're careful about tracking it, that's how it's hard to implement, right? Then you can update your information using Bayes' rule. This is Bayes' rule. Yes?
So on the right-hand side of the equation, B is raining, or sorry.
B is rain, yes, B is rain. In my little discussion right now.
Okay, and on the left-hand side of the equation, B is also rain?
Yeah, so the way you say this is you say, this is the probability of rain given, right? This bar means given, right? Something else happened.
Which is cloudy in this example.
Yeah, or maybe we would say, I mean, cloudy's kind of silly because it's not gonna rain if it's not cloudy, right? But maybe we make maybe we say 50% or more cloudy, to be a little more specific, right? Or 75% or more cloudy, right? Or maybe we say
Thunderstorms.
these type of clouds in the sky or something, right? So on the days when it rained, how often were those types of clouds in the sky? We could know that, right? If we kept track carefully, right? So we could know the likelihoods. So when we see that type of cloud in the sky, we can use the prior probability of rain. Let's say the weather forecast said there was a 60% chance of rain, right? And we can update it using this formula to get the new probability of rain given what we saw. Okay? So here's the main point I want to make. Not so much the example, but I'm adding information to my current probability to update it and get a better, more accurate probability. That's basically what Bayes' rule does. And it's a really, really hot technique. There's a bunch of analytical techniques that even in R we could have covered that involve Bayes' rules, so it's useful. So let me go back to this tree and then we'll try to solve this problem and then we'll get out of town. Here, we have a priori or prior probabilities of if our product's going to be successful or not, right? We have prior probabilities. Why do we have prior probabilities? Oh, chapter 14. Why do we have prior probabilities? Because we've rolled out a bunch of products in the past and we know on average 30% of our products are very successful, 40% are moderate, and 30% are very successful, 40% are moderate, and 30% are total failures. Those are our prior probabilities, not knowing anything, right? It's our history. So those are our P of B's, so to speak, right? For products that were successful, very successful, how often did the focus group say they were successful? We can be keeping track of that, right? We can know how accurate our focus groups are. So we can know these likelihoods. How often, for products that were very successful, how often did they say they were moderately successful? We can know that, right? So we know those likelihoods from our historical data. So these probabilities, these posteriors, are actually these probabilities right here, because now they told us the product would be very successful.
Sorry?
Okay?
Do you want to send the quiz?
Oh, thank you. We know these probabilities we're going to be very successful, right? We know they said very successful. How likely is the product to be very successful? So these probabilities up here are actually going to be posterior probabilities, okay? I've got it queued, so let me just send it real quick, and I'll get back to the lecture. All right?
Right, meow.
So the biggest, trickiest, hardest thing of all this is pulling out all the probabilities and attaching labels to it. I'm sure all of you can follow a formula if you're forced to, right? That's not the issue. Computer, go. Perfect. Thank you very much. Did she email you?
No.
Oh, good man. Let's see. 502, perfectly. All right. She got better service than you did. Sorry about that. All right. Okay. So here's the only other thing I'll say. Sometimes you can use Bayes' theorem directly, because ultimately you are going to be given all these numbers. You just need to figure out how to attach labels to them. Okay. And I'm going to try to teach you that right now. You're going to be given all these numbers. And you're going to want this number, right? Actually, I have a spreadsheet that's kind of a cookbook that'll help a little bit, okay? But as an intermediate step, Bayes' rule symbolically, Bayes' rule takes you from conditional probabilities that like A given B and changes them into B given A, right? You can go through this middle step if you want. It might make it easier for you. And the cookbook way I'm going to give you does go through this middle step. The middle step is just using, if I'm given A given B, if I'm given A given B, and I'm given B, I can calculate A and B, right? This formula here is the same as this formula here, just rewritten, right? So I can calculate these things if I want to, calculate that table. Once I have this table, I can do A given B or B given A using the formula, okay? So you can use Bayes' rule as a straight up rule, or you can go, there's different ways you can finally calculate this posterior. All right? I'll leave this here, you can take a picture of it later, but let's try this on this problem. All right, and we'll go through it. This is one of the classic Bayes' rule problems in the world, actually, and very relevant for anyone who's ever had to go through any kind of serious medical situation. Unfortunately, or had a relative that has, which I'm sure we've all experienced at some level. So let's try it. All right, step one in all of these problems is you're going to have two events. You have to have one event that you're kind of interested in and another event that gives you information about that other event. So there has to be two events. So step one, I'll give you a little cookbook here. Step one is give labels to the events. All right, once you do that, then you'll do step two. I'm making this up as I go, by the way, but I think it's good. Give labels to the event. Step two is determine the given probabilities. Not always easy either. And step three is what are they asking for? So it's also a probability in these problems. And then finally, step four is to make the calculation.
You said what are they asking for? You mean
What's the question say? Okay? The thing is what I want you to do though on these steps, I don't care really what order you do these last two steps in, but what I really care about is you've got symbols to write things down in, not words, right? Because once you have symbols, then you can go, okay, I got this formula, I can pop it in this formula, and I'm ready to go. All right? So suppose the probability that someone in the general population has a certain disease is 3%. A test has been developed for this disease. The test has been shown to indicate a positive result, that is that the patient has the disease, when someone does actually have the disease 90% of the time. So when you have the disease, it shows a positive result 90% of the time. However, the test also shows a positive result when someone does not have the disease 2% of the time. In other words, the test gives a false positive. Okay? So that's all the information that's given. It's a fairly simple problem in terms of the amount of information. What are the two events?
Positive and negative.
Okay, positive and negative what?
Result of the test.
Okay, so let's call that T, positive test. That's good, positive test. And let's call it T complement for negative test. Okay, that is an event, right? Okay, you got one of them. What's the other event in this
T
problem?
positive, negative.
So this is a positive test, this is a negative test.
I mean, T false, no, yeah, that's what I mean. False T.
Know whether somebody has the disease or not.
Bingo. Whether somebody has the disease or not. So D will be has disease, and D complement will be not have disease. Okay, so we've got our two events. Notice the test gives you information about whether you have the disease or not, right? At least you hope it does, otherwise why are you doing it? We have a problem in the United States, by the way. The doctors order all sorts of tests all the time because they make money. Or they cover their butt as far as insurance goes. One or the other.
Will be sent down.
All right, so what do we know? What events do we know the probabilities
Know
of?
the probability.
90% or positive?
Okay, so 90% equals probability of,
But it's conditional. It's 90% when the test is positive. So it's
Given D.
the test has been shown to indicate a positive result
it's D given T.
when someone does actually have the disease 90% of the time. So the hard thing is the word given isn't in there anymore. Where's the given?
It's D given T.
Given is like has the disease.
Okay? Yes, exactly. When someone does, oops, little problem by the teacher. When someone, I'm glad Jacob's not here. When someone does actually have the disease, cross out has, okay? Sorry, now I know why students have been confused on this for years, okay? So is it T given D or D given T?
T given D.
It's T given D, that is correct. Okay, so that's hard to figure out, right? So notice it says, substitute the word given, right? Given someone has the disease, the test shows a positive result 90% of the time. So pop the word given in there, and that'll help you to get the right condition. So just remember, given, okay? What else do we know?
2%.
Keep going, you're doing good.
2%, which is T given D complemented.
2% is the probability of T
given D complement.
given D complement. What do you guys think?
Yes.
Right? The test shows a positive result when or given someone does not have the disease 2% of the time. Okay? Good? Anything else? Generally, by the way, you're gonna be given 3 probabilities, is another big
That's
hint.
a 3%.
Yeah, what's the 3%? That's right, there's another number there, right? It's a math class at some points, right, where you use all the information.
Probability of
D.
Probability of D, very good, so 0.03, probability of D. So to go back to the earlier terminology, right, this is the prior, right? If you don't have a test, you got a 3% chance of having this disease, right? Now what are we really interested in? Let's go straight to B, and I'll explain A to you in a minute. Let's go straight to B, okay? If the test is positive, what is the probability somebody actually has the disease? So how do I write that down in symbols?
But what is the probability of?
That's the 0.5, 0.05.
Be careful. I want the symbols first, and then we'll work through the answer.
Probability.
There's a 9%, 8% yes.
Probability of D given T.
Okay, so QB is asking for the probability of D given T. Can you see that? Can you see that?
What's QB?
Question B. Sorry. All right. Right. If the test is positive, given the test is positive, right? So notice, we have the prior, probability of somebody having the disease in general. Now we have a positive test result. How do we update the probability that someone has a disease? Okay, so this is common situation, right? So we call this the posterior, right? After we've done the test and we've got a positive result, what is the probability someone has a disease? So now we can solve this very straightforward. We've attached everything to symbols. We can plug everything into Bayes' rule and be done. Okay? So I'll just write down Bayes' rule. P of D given T is equal to P of T given D times P of D divided by P of T given D times P of D plus P of T given D complement times P of D complement.
How do you know whether we use this formula or a simple formula when for the conditional?
Yeah, so good question. So the way you would know, right, is we're looking for D given T, and we've given T given D and T given D complement. The conditional split, right? That's the way we would know. If you're given joint probabilities, Michael, then you can use the direct definition, all right? And we'll do that real quick when we finish this. All right, just by the way, before we actually plug in numbers, you know there's a 3% chance that someone has the disease in general, right? If you have a positive test, what do you think that probability goes up to? Do you think it goes up to 90? Is it more like 70? Is it 50? Is it 40? What is it?
90.
90, okay? Let's check, right? In some sense, think about it. In some sense, these measures right here, these likelihoods, right? Remember, you looked at all people who had the disease and you saw how often that test was telling them they had the disease, right? You know this is the historical accuracy of the test. Or in all those things when they didn't have the disease, you know how many times the test gave a positive, right? So you would kind of know these things, right? Or the drug company probably would, right? So these are sort of the reliabilities, if you will, right, of the test, right? These are like reliabilities. We call them likelihoods, but they're like reliabilities. All right? Well, this is just plugging in, right? So I got 0.9, right, on the top, times 0.03. I might need your calculator skills here in a second. 0.9 times 0.03, and this is divided by the same thing, 0.9 times 0.03 plus 0.02 times, what do I put in for D complement?
The complement is 1 minus D.
Yeah, so it's 0.97. Can somebody calculate that real fast? I don't know if you get the right number, but I can't remember what the number is off the top of my head. That sounds right. 0.58. So there's a 58% chance that you have the disease. So it was 3. The probability of having the disease has gone way up, but it's nowhere close to 100% sure. Okay, that's one thing that's interesting here, I think. Even with a 90% reliability here, right? It's nowhere close to being sure. It's only 58%. Okay? And again, that has to do with the fact that these tests aren't perfect. Notice that if this were 0 and this were 100%, right? This would be 1, this would be 0.03, this would be 1, this would be 0.03, this would be 0, and this wouldn't matter, right? So we'd have 0.03 over 0.03, we'd have 100%, right? But these numbers look pretty good, but they still only bring us to a 58% chance of having the disease. Okay? So this is an example of Bayesian updating. All right, we're going to do this in a bigger context later. Let me just mention.
Oh, can I take a picture first?
Sure. Sorry.
So it means that if I get a test which is positive, it's only 58% that I got the disease.
That's right. So what's the doctor going to generally say?
But then why do you do a test?
Well, but isn't it better information than you had before?
It's 8% better than before.
Yeah, it's quite a bit better than before, right? What's the doctor going to say next?
Do other
We need
tests.
more tests.
Do more tests. That's what they always say, right? We're going to do more
But I don't
tests.
think they know the reason behind it.
I think they do implicitly, but I don't think they know the exact numbers. I'm with you there, right? Okay, just to point out one other thing.
So in order to calculate the actual success of the test,
Yeah,
so they do more side tests. In order to come up with the 90%, they should have done a lot of more tests, because
Yeah.
otherwise how can they say that he indeed had the disease and we managed to find the disease?
well, remember too, that the test wasn't always designed to test for that disease. It might have been test a bigger class of diseases, right? I mean, things like cancer are, really, really, really complicated and wide. There's lots of types, it's more a name for a general class of ailments, right? So maybe, for example, I might do a PSA test as a middle-aged man, right? Which is for testicular cancer, right? But they might find something weird in that test that leads them to some other kind of situation, right? So that may be part of the reason. But these numbers look pretty good to me, but it turns out they don't lead you to near 100% chance of having the disease. So just one other thing, right? We were given these 3 quantities. I'll write down the joint table just to leave you with this thought for today. We've got D and D complement, T and T complement, right? This is P of T and D and T, right? Which we can write as T given D times P of D, right? Which would be 0.9 times 0.03. I think I can even do that in my head. This is 0.027. Okay, I'm just going to fill in this table. And we already know P of D, 0.03, so this one has to be 0.003 because those have to add up. Now we're also given this one. So this one looks like this one, P of D complement and T. So that's P of T given D complement times P of D complement. So that's 0.02 times D complement, 0.97. So what do I want to say here? Equals 0.0194? Something like that?
Something like that.
Okay, so if I add these up, I get 0.04. Yeah, 64. Okay, right? And down here, I'm going to get 0.9536, 1, 0.97.
First
first one should be smaller. Should be something like 2 to 1. In the first one, you add by row, right?
Yeah, you add by row, you add by column.
Yeah, so you have 0.027 added to.
0.003.
Sorry, minus.
Yeah, 0.003. I think I got it right. And then this one is 0.9506. I recognize these numbers from before, so I think these are right. So my point is this. I just computed the joint probability table for T and D. You didn't really need this in the problem, but now if I want D given T, like I do, I just do D and T divided by P of T, right? D and T is right there, 0.027, and probability of T is right there, 0.0464. If you divide these two, I'm pretty sure you're gonna get 0.58 back again, okay? So another way to do this is to calculate the joint table first, right? And then calculate the second conditionality. You're really doing all the same steps, but it's just another way to calculate it. Some people find this more natural to do it this way. Maybe because that's the way we generally teach probability in the first place. So you can see the answer to part A actually is there's the percentage of positive tests, forget whether they have the disease or not. The percentage of positive tests is about 4.6. The percentage of negative tests is 95.4. All right? Okay, what time is it?
5:22.
5:22. Do we have any questions on this before we leave it? Okay. We'll go back over this a bit tomorrow. So in the context of decision trees. So in the context of two-stage decision making.
Okay.
So when we do that, right? But again, you have, just summarize, you have two events, right? One event informs about another event, right? If you don't have any value for the one event, if I haven't looked outside yet today, all I can base my weather forecast on is what the news said last night, right? That's my prior. Once I look outside before I go to work or wherever I'm going, right? I get some additional information, and then I update my probability with that additional information, right? The doctor updates the probability that you have a disease by doing a checkup or by doing tests, right? After they update the information, then they give their diagnosis. Are they 100% correct? No, not always, right? They could be wrong very easily, right? And that's why very often they want to collect additional data and do additional tests. And even then, doctors have known to be wrong, especially if the ailment you have is relatively rare, right? There's good reason to believe why we might know these likelihoods if we were tracking these things, right? On all days, when it rained, what did the sky look like, right? On all days when it didn't rain, what did the sky look like on those days, right? So if we were diligent, you know, we could keep a little table at home with this. Nobody does that, right? So it's kind of hard to actually be a Bayesian in practice, right? But you could actually track this stuff, right? And you could actually update the weather forecast. My father's one of his whole shticks when he was alive, and he passed away quite a while ago now, like in 1997, so like 20 years ago. His whole shtick was that weather forecasters should use scientific data, right, to make their prior, but then they should use subjective data to update their prior to get a better forecast. Scientists didn't like this very much. Scientists like to use real data. I see the scientists, they're smiling. They don't like subjective information. But the cool thing about Bayes' theorem is that you can incorporate additional information and get a better estimate. At least that's what Alan Turing believed, and that's what Nate Silver believes, right? Now, Nate Silver was famous because he predicted every state correctly, I think except one, in the second Obama election. And so everybody was looking to him in the first Trump election, and he was wrong, like most people. However, he was less wrong than most people. He had it like 49-51. Most people had it 45-55 or something much further apart. And actually, a couple days before the election, he said it was a toss-up.
So basically it was pretty much.
He was closer than everybody else. Now, of course, it's a binary decision, so after it's over, you're either right or you're wrong, right? But it's interesting. He actually speaks at a conference that I've attended a few times, a sports conference, And he really got hammered last year at the conference because, I mean, nobody thought Trump was even gonna win the primaries, right, the pre-election elections. And he won those, and then he went on, of course, to win the election, so. But he uses these methods in trying to do his forecasting. All right, that's it. Have a good Saturday. Let's go have a beer if you want. I'm up for it. If you guys want to join us for a beer, you can come.